Very often we're going to be confronted with situations where instead of just wanting a marginal probability or the probability of some event, we're going to want the probability of some event, but we have other information that we want to take into account. And so having tools that are going to allow us to use all of the information that we know is going to allow us to be a lot more flexible with our probability modeling. So often we will have further information that's going to shift the likelihood of different events. These probability shifts can be understood through a topic known as conditional probability. And so what is conditional probability? Well, the marginal probability of any event is the probability that a single event actually occurs. So marginal probabilities refer to one single event. Joint probabilities are going to refer to two or more events occurring simultaneously. And so if you want the joint probability of some events, then we're looking at, well, what's the probability that all of those events occur at the same time? A conditional probability is going to be the probability that an event occurs given some additional information. And so then by way of notation, we write down the probability of A given B. So this is the conditional probability of A given B. And we think about this as asking, well, what's the probability of A given that we know that B has occurred? So the event B we know has occurred. We want to know, well, what's the probability that the event A also occurs? So if we know that B has occurred, what is the probability that A also occurs? So consider the following examples, and in each of these examples we can think about, well, what would a marginal probability look like, and then what is a joint or a conditional probability going to look like? So we can ask ourselves, well, what's the probability that it rains today? That's just a marginal probability. But what if we look outside and we know that the skies are gray? So if we want to know, well, what's the probability it rains today given the skies are gray, this is now a conditional probability. We have additional information. This information is going to change our belief about the world. It's probably more likely that it rains today if the skies are gray compared to if the skies are not gray. Right? And so that's a conditional probability statement. Now, what's the probability that it snows today? Again, we could think about this as just a marginal probability. But what if we know the information that it's August and that we live in Canada? Okay. So given that it's August and living in Canada, the probability that it snows today is going to be quite small. If we don't know that piece of information, then perhaps the probability is quite a lot larger. Right? So we have to think about, well, what information do we have? And the conditional probability is going to take that into account. Now, what's the probability that you ace an exam? Right? We can just think about that as a marginal probability, and that's going to depend on, perhaps you have a unique probability for yourself. You've taken some number of events or exams in your life, and you've aced some number of them. But what's the probability you ace an exam given you did not study? If we know the information you did not study has an added piece of information, that's going to change our belief about the probability that you ace the exam. As a final example, what's the probability that a number rolled on a die is a 2 given that it's even? So if we're told that a number is even, then we can think about, well, what's the probability that it's actually a 2? And of course, the probability that you roll a 2 without knowing anything is just 1 out of 6. But if I tell you it's an even number, then intuitively, there's a higher chance that it's going to be a 2. Right? So we can think about conditional probabilities as capturing these types of pieces of information that we might know about the world around us. Now, intuitively, we know what a conditional probability is, but how do we actually go about calculating them? And so if we have two events, A and B, and we know that the probability of B is greater than 0, then what we can say is the probability of A given B, so the conditional probability of A given B, is the probability of A and B, it's our joint probability, divided by the marginal probability of B. Right? And so this is going to be how we define our conditional probability. If instead we wanted to look at the probability of B given A, so what is the probability that B occurs if we know that A has occurred, we use the same definition, except we change out the denominator to be the probability of A. And so importantly, the denominator, the event that we condition on, and the denominator have to match, right? Condition on A, probability of A, condition on B, probability of B. Now note that the joint probability is actually symmetric, so the probability of A and B is the same as the probability of B and A, and so the numerators never change in our definition here, just the denominators do. It's also important for us to remember that the probability of A given B is not going to be the same as the probability of B given A, at least not in general. And one really concrete example that we could use to think about this is, well, what's the probability that you roll a 2 given it's an even number? Right? And we could work out what that is. versus what's the probability that it's an even number given that you've rolled a 2. If I tell you that you've rolled a 2, well, then you know it's an even number. And so those have to be different probabilities there, right? So these events are different, A given B and B given A, and as a result, we have to treat their probabilities differently as well. Now, if we wanted to start looking at some examples, let's take a look at the example of rolling a 2 given that we know an even number. And so what is the probability that the die shows a 2 given that we've actually seen an even number? And there's really going to be two approaches that we can take with any conditional probability question, and sometimes one of them is going to be easier than the other. The first one that we can take is just to go back to our definition, right? So if we want the probability of A given B, that's going to be the probability of A and B divided by the probability of B by itself. And so in this case, right, A is referring to the event that we roll a 2, B is referring to the event that we roll an even number. And so what is the probability that we roll an even number that is also a 2? Well, 2 is an even number, and so this is just simply the probability that we roll a 2, right? And so in the numerator here, we have 1 out of 6, okay? And then the denominator, the probability of B, that's the probability that we roll an even number, that is going to be 1/2, right? And so we have 1/6 divided by 1/2, and so that should give us 1 in 3. Okay, so that's the first approach that we have that uses our definition. This will always work. Now, sometimes what's actually easier for us to think about is to take the information that we have and to actually rewrite our sample space. And so if we roll a die, right, we know that we have this sample space of 1, 2, 3, 4, 5, 6. Those are the possibilities. But now I've come in and I've told you, you've rolled an even number. Okay, and so the sample space is no longer the full sample space we're looking at here. Instead, we can cross out the 1 because the 1's not an even number. We can cross out the 3 because that's not an even number. And we can cross out the 5 because that's not an even number. And so in some sense, we can think about this new sample space that we have here as being the 2, the 4, or the 6. And notably, this is just the event B. This is the event that we've conditioned on. We know that B has happened, and so we can treat this as our new sample space, right? We have our new sample space going here. And then what we're really asking ourselves is, well, given this new sample space, what's the probability that we rolled a 2? And there's only 1 2 here, right? There's 3 events. They're all equally likely, and so that has to be 1 out of 3. And so either you can think about the definition of conditional probability, or you can think about conditional probability as effectively reducing the sample space. And both are going to be valid approaches. Sometimes one is going to be a lot easier than the other to use. Okay? And so we're told that the number, that it shows an even number, and so we can think about our sample space as being a 2, a 4, or a 6. Each of those is equally likely, so the probability of A given B has to be 1 out of 3. Alternatively, we could compute this directly. The probability of A and B is 1 out of 6, because that's just the probability we roll a 2. The probability of B is 3 out of 6. It's the probability we roll an even number. And so then A given B is the ratio of those two quantities, so 1 out of 6 divided by 1/2, which is 1/3. And so if we condition, we're effectively reducing our sample space, and sometimes that's a really useful way of thinking about the problem. So let's take a look at another example here. We're going to roll 2 dice, right? And we're told that the sum is 10. So what's the probability that at least one of them shows a 6? And again, we can think about doing this in one of 2 different ways. So the first way is to think about what is our reduced sample space. Okay, so the reduced sample space here, we know that the 2 dice have to add up to being a 10. And so what are the combinations on 2 dice that can give us 10? Well, you can't roll a 1, you can't roll a 2, you can't roll a 3. Right? Because if you roll a 1 or 2 or a 3, then you'd need a 9, an 8, or a 7, and that doesn't work. And so the first die might show a 4, which would mean the second one would have to show a 6. The first one might show a 5, which would mean the other one would have to show a 5. Or the first one might show a 6, and the other one would have to show a 4. Okay, and so those are the only possible options for our reduced sample space here. We want to know what is the probability that at least one of them is showing a 6, and so we can get a 4 and a 6, or a 6 and a 4. And so the probability of A given B in this case has to be 2 out of 3. Right? We have our reduced sample space here. 2 of the 3 options show at least 1 6. Now, how else might we have done this? Well, we could have said that the probability of A given B is going to be the joint probability of A and B divided by the probability of B. Okay? In this case, A is the event that the sum is, or that the at least 1/6 shows, and B is the event that the sum is 10. Okay, and so how many different combinations are there in total? Well, there is a total of 36 combinations. Okay, how many ways can we have A and B both happen? So at least 1/6 is shown, and the sum is 10. Well, the only two ways to do that are to get a 4 and a 6 or a 6 and a 4, right, which we have drawn up here. So that's going to be a 2. Alternatively, how many ways can B happen by itself, right? So how many ways does B happen? Well, you need to roll a 10, a sum of 10, and we see that there are 1, 2, 3 possible ways that B can happen. And so then the other option that we have here is to note that this is going to be 2 out of 36 divided by 3 out of 36, which is 2 out of 3. Right? So again, we can either do this via direct calculation or by making a reduction in the sample space argument. So we can see this argument play out, right? Because we are told that the sum is 10, we can treat the sample space as though it were just the event B, right? It's a 4, a 6, a 5, and a 5, or a 6 and a 4. Each of them is equally likely, so we get the conditional probabilities 2 out of 3. Alternatively, there are 36 total pairs of dice. The probability of A and B is 2 out of 36. The probability of B alone is 3 out of 36, and so their ratio gives us 2 out of 3. So direct calculation or sample space reduction, both will work here. Now suppose that we consider a standard deck of 52 cards. If we draw a card at random and see that it is red, what is the probability that it is also a heart? Okay, and so here we can either think about doing this intuitively or we can do this out directly, right? So if we are seeing a card, I picked out this card and I'm looking at it and I tell you it's a red card, what's the probability it's a heart? Well, half of the cards that are red are hearts and half of the cards that are red are diamonds. And so we know that that probability has to be 1/2. But how might we get that directly? Well, the probability that a card is red is 1/2. The probability that a card is red and is a heart is the same thing as saying the probability that it's a heart, because all hearts are red, and so that's 1/4. And so then we take 1/4 out of 1/2 to give us our 50% chance. Right? So we can get that intuitively, or we can get that directly. Now, if we draw a card at random and we see that it's an ace, what's the probability that it is a heart? Okay? So I've pulled out a card, I'm looking at it, I tell you it's an ace. What's the probability that it's a heart? Well, there are 4 possible aces. One of those is the ace of hearts. And so we know it has to be 1 out of 4, but we can do this directly. Right? The probability of an ace is 1 in 13. The probability that something is an ace and a heart is 1 out of 52, right? Just the ace of hearts satisfies that. And so if we take 1 out of 52 divided by 1 out of 13, that gives us 1 in 4. So it's the same as what our intuitive probability there has to be. Now, if we draw a card at random and we see that it's a heart, what's the probability that it's red? So I'm looking at this card. I tell you, this is a heart. What is the probability it's red? That probability has to be 100%, right? Because all hearts are red cards. And so it must be 1 because all hearts are red. But if we wanted to do that formally, the probability that it's a heart is 1 in 4. The probability that it's a heart and it's red is also 1 in 4. And so the ratio of those gives us a 1. Now suppose that we draw 2 cards at random. What is the probability that they are both aces given that at least one of them is an ace? Okay, and so here we probably just want to do this one directly, right? We want to know, well, what's the probability that both cards are aces? So A is both being aces, given at least one is an ace. That's B. So that's the probability of A and B divided by the probability of B. Okay, and so if we want the probability that both cards are aces and at least one of them is an ace, this right here is the same thing as the probability of A by itself, right? If both cards are aces, at least one of them is an ace. And how can we do this? Well, we know that has to be the number of ways that you can get 2 aces divided by the total number of 2 card hands, right? So how many ways can you get 2 aces? Well, there are 4 aces in the deck. Choose 2 of them. How many ways can you get 2 card hands? Well, there are 52 cards in the deck. Choose 2 of them. Right? For probability of B, this is the probability of at least 1 ace. Okay? And so how might we do this? Well, we can either break this down into exactly 1 ace or 2 aces, but it's easier for us to realize that this is 1 minus the probability of B complement. Okay? And so if you wanted the probability of B complement, well, that's going to be 1 minus the ways that we can get 0 aces. And if we want 0 aces, then what we have to do is we have to pick 2 cards that are not aces. 48 of the cards in the deck aren't aces, and so that's going to be 48. Choose 2 out of 52. to choose 2. And then if we take the ratio of these probabilities, that's going to give us our response here. Okay, and so we can look at this, right? And on the slides here, we'll have a slightly different approach to the problem, but it's the same logic. Right, there are 52 choose 2, which is 1326 total 2-card hands. 4 choose 2 of those have 2 aces, right? So that's exactly the same. But then 48 choose 2 of those have no aces at all. And so if we know that 1128 of them have no aces, then 1326 minus 1128 of them, which is 198, have at least 1 ace. And therefore, we take 6 out of 1326 divided by 198 out of 1326, which gives us 1 in 33. So there's a 1 in 33 chance that if we draw 2 cards at random and we know that at least one of them is an ace, that they're both aces. Now we'll consider a related question here. Suppose that we draw 2 cards at random and we see that the first one is an ace. What is the probability that they're both aces? Now, intuitively, the way we could think about this is we're dealing cards out of a deck of cards. We deal the first one face up and we see it's an ace. And we're asking, well, what's the probability that the next card is still an ace? Okay. There are 3 aces left in the deck. There are 51 cards left in the deck. So we know this has to be 3 out of 51, or 1 in 17. Right? After the first card's an ace, we have 3 aces remaining. There are a total of 51 cards remaining, so it must be 3 out of 51, or 1 in 17. Now, we can do this directly as well. There are 52 cards in the deck. We want to take sequences of 2 of them, and so that's permutations, right? We take a total of 52, subset of 2 of them, which gives us 2,652 total sequences there. Of these, 12 of them, so 4 times 3, have both aces, and then 4 times 51, or 204 of them, are going to have the first card being an ace. Okay, and so then we can take 12 out of our total, divided by 204 out of our total, which is 12 over 204, which is 1 in 17. So we get the same answer, whether we do it sort of through intuition or by directly calculating it. Now, the question that we have is, why are D and E not equal? So we think about what we're saying. In D, we said the probability that you have 2 aces, given that at least one of them is an ace, is going to be 1 out of 33. The probability that you have 2 aces, given that the first one is an ace, is 1 in 17. So why are those not the same probability? And so it's worth us thinking about our reduced sample space for a minute here, right? And so in that first case, if we think about what our sample space is going to look like, we can be in a case where we have an ace and an ace, right? That's the case of 2 aces. We could be in a case where we have some card and then an ace, or we could be in the case where we have an ace and then some card, okay? Now, what's important to note here is that these 3 events are not equally likely, right? Because X here can be any number of cards and the X here can be any number of cards, but these are the 3 patterns that are possible. Now, in this case in part E, what patterns are possible? Well, we can still have the ace and the ace, but the X and the ace is no longer a possibility, right? We cannot be in a case where we have an X and then an ace. And so then we're just left with this case of an ace and then an X. Okay, and so as a result, there's actually fewer cases in this sample space that do not have the same ace-ace pattern. And as a result, we have a higher probability of them both being aces if we know that the first one is an ace versus if we know that simply one of them happens to be an ace. Okay, and so it's a little bit strange, but that's the idea. Knowing that the first card is an ace gives us more information because it's not possible that we have an X and then an A. So something that's not an ace and then an ace, whereas in D, that was actually possible. The probability becomes more certain. Now, this same sort of principle can apply in something that is a little bit strange. It's called the two-child problem. And so suppose that the sex of a child born into a particular family is random, and it's equally likely to be either female or male. So if a family has 2 children, then it's equally likely that we observe a female-female, female-male, male-female, or male-male. Now, suppose that we are considering families that only have 2 children, and then if a specific family, we know that the younger child is female, we can ask ourselves, well, what's the probability that they're both female? And so we could either do this calculation directly, or we could think about this through our reduced sample space. And so I'll write out the reduced sample space argument here. Right, in the reduced sample space, we know that the younger child is a female, so that allows us to have a female-female or a female-male. Right? The other 2 possibilities are not going to be allowable. They're all equally likely, and so in this case, we can say, well, one of those has 2 females, there are a total of 2 possibilities there. So the probability here has to be 1 out of 2. Okay. Now we could do this directly as well, right? If we wanted to calculate this out directly, well then the probability of B, right, which is that we have the younger child being female, the younger child is female, is going to be 2 out of 4 because we have female, female, and female, male, right? So that's 1/2. The probability of A and B, which is that both the younger child is female and both children are female. Well, the only way that happens is if we have 2 females. So that's going to have a 1 in 4 probability. And so then we can take the ratio. 1 out of 4 gives us 1 out of 2. Right? 1 out of 4 divided by 1 over 2 is 1 over 2. And so we either can do the direct calculation shown on the slide here, or we can do the sample space reduction. Either way, that's going to result in a probability of 1 in 2. And this makes some intuitive sense, right? If you're looking at a family, you know they have 2 kids, they tell you their younger child is a female. What's the probability that both of them are female? Well, that's just asking what's the probability that the older kid is female, right? And there's a 50-50 chance that that happens in our simplified view of the world here. Now let's look at a related question, but let's see if there's anything different about it. So suppose that we ask the parents of the family with the 2 children whether they have any female children, and they respond yes. Now what is the probability that both children are female? So once again, we can either think about doing this by sample space reduction, or we can think about it through direct calculation. And so I'll write down the sample space reduction case here. What is the information we know? Well, we've asked them, do you have at least 1 female child? Do you have any female children? And they say yes. And so we can be in the case where they have a female and a male, or a male and a female. Those are the 3 cases. All 3 of those cases are equally likely. And as a result, 1 out of 3 of them has both female children. So the probability in this case is going to be 1 out of 3. Right? We can also do this calculation directly, and so we'll walk through this here. Right? In this case, the probability of B is going to be 3 out of 4. Right? So the probability that at least 1 child is female is 3 out of 4. Female, 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 male, male, female. Right? 3 of those 4 events. Probability of A and B, so the probability that at least 1 is female and both children are female, well, that's just both being female, right? So that's 1 in 4. So 1 out of 4 divided by 3 over 4 is 1 out of 3. So why is this the case? Well, it's exactly the same as the card example we just saw, right? In this part B, we're presenting the option that we have a male and then a female child, whereas in part A, that is not actually going to be a valid option, okay? And so the MF outcome is the one that is missing. This is the same thing as when we have those 2 card case. And this seems really strange on first glance, right? Because we're going to be in the situation where if I tell you that the younger child is female, that's giving you more information than if all I tell you is that at least 1 child is female. This is really strange, but it also shows us why it's really important for us to actually mechanically work through these things and to really think critically about what information do we have and what information are we looking for. Okay, so conditional probabilities are going to be an incredibly powerful tool. We'll use them all over the place. And what they allow us to do is integrate additional knowledge that we happen to have into our probability calculations. So anytime that we know something about the world, anytime that we're able to observe something about the world, we can take that into account through the use of conditional probabilities and through the use of this conditional logic. We can rely on our definition of conditional probabilities, which joins up joint, marginal, and conditional all together. Or we can sort of reason our way, either intuitively or through this idea of sample space reduction. And these are all going to be effective ways of solving problems in conditional probability. But conditional probabilities are going to be a really useful tool when we're trying to model the real world using the information that we actually have around us.